And we are live. Okay. Good morning, everyone, and welcome to the new episode of Cogito 137's Nobel in Focus, a series where experts explain the science behind the discoveries that were awarded with what is considered to be one of the greatest honors in science. I am Isha Bhagwat from IISER Kolkata, along with Aditya Dwarkesh, who will be acting as the moderator for this session. And we have a guest speaker today, Dr. SSV Ramasastry. Dr. Ramasastry is an associate professor in the Department of Chemical Sciences at IISER Mohali, and his research work mainly revolves around the field of organic synthesis and catalysis. Welcome, Dr. Ramasastry. It's an honor to have you
Thank you.
here, and we are really excited to hear your talk.
Okay, so I can start.
Yes.
Okay, thank you very much, Isha. I'm especially glad that I've been invited for this particular privilege. Obviously, that it's a privilege because I'm talking about some noble science. So today, I'm of course going to talk in a short manner the science behind the Nobel Prize in Chemistry 2021. So we all know that the Nobel Prize this year was awarded to Professor Benjamin List from Germany and Professor David MacMillan from USA. So this for their contribution to the development of asymmetric organocatalysis. Okay, this is what was cited by the Nobel Foundation. So what we'll try to do is before we actually talk about the real science behind the Nobel Prize, I'll very briefly talk about what is asymmetric synthesis and why it is important to prepare molecules chiral, what is organocatalysis. These three questions I'll address very briefly, and then we'll move on to the actual topic. Okay, so uh, in this regard, so whatever is in and around us that nature created are chiral molecules. So as you see, the essential building blocks such as carbohydrates, amino acids, enzymes, and of course DNA, although the element of chirality in DNA is different compared to the other three that I listed here, these are the essential molecules that we are all made up of, indeed nature is made up of. So, in addition to this, nature produces natural products. Many of them, or most of them, are chiral in nature. Okay. In addition, the drug molecules. So, in many instances, they're artificial or synthesized molecules. Drugs, I mean to say, the medicines that we take usually. For example, I listed a few, for example, bronchodilator, CNS stimulant, peristaltic stimulant, antidepressant. These are the molecules you identify readily that these molecules have stereogenic centers or otherwise chiral centers. Okay, just as those natural products that we regularly come across being chemists. Okay, followed by this, the next question that I'm going to address is why synthesizing molecules in chiral form is important. Okay, so of course we appreciated what nature does. It of course produces molecules in chiral, but when it considered synthesizing, whenever there's an opportunity to synthesize, why it is preferred to perform this operation in chiral. So I take a couple of examples in this regard. Okay, for example, you see this warfarin, which is a drug used for anticoagulant activity. Okay, you see the molecule; it has one chiral center. You see this particular site where I put a star. That's a stereogenic center. So obviously, we understand that a molecule having a stereogenic center in this particular instance, you can understand that it's composed of two enantiomers, that is one R enantiomer and S enantiomer in equal composition. So what was identified as of this warfarin after particular research was that the S enantiomer was about 3 to 4 times more potent than the R enantiomer. What that means effectively is, if you take, for example, 100 milligram tablet of S enantiomer, it's equivalent of 300 to 400 milligrams of the R enantiomer. So that tells you which one. Obviously, that dosage ideally should be as less as possible. So that tells us that preferred one would be to synthesize the S enantiomer than the R enantiomer. Okay, so followed by this, I have another example that is a pterodyline. This also has one stereogenic center. Purposefully, I took simple examples so that I don't give any confusion as of the details that are concerning these enantiomers. Okay, so as of this pterodyline, this also has one stereogenic center and two, obviously, enantiomers, one R and S. Okay, this drug was used for the treatment of urinary incontinence. Urinary incontinence effectively means the lack of control on the urine passage. Usually we see this, I mean, usually, although this is prevalent in all age groups, usually we see this occurring in kids and elderly people. But what was eventually realized was the R enantiomer, that is the first one that is mentioned here, was having severe cardiotoxic effects. So compared to the S enantiomer. So we underestimate the properties of enantiomers. We think that they're very closely related, just one center is opposite. Okay, so for example, if you compare R and S, just one center is opposite to one another. Despite the fact, you can see how significant impact that it is leaving on biological systems, such as us, in this instance. Okay, it leads to cardiotoxic effects. So with these two, I move on to the next question. Of course, one can definitely go through what I mentioned at the bottom of the slide. That is the thalidomide story, which is very well known, and due to the paucity of time, I'm not talking about it, but one can go through, and that makes us realize why it is significant making compounds in chiral, especially those which are biologically active. The next question I asked in the beginning, what are the modes of introducing chirality? There are different ways. Okay, prominent ways are the substrate controlled asymmetric synthesis, auxiliary control. This also falls under substrate controlled asymmetric synthesis, but auxiliary is something removable functionality in a given molecule. Okay, and then comes a reagent controlled asymmetric induction. Most importantly, and most atomeconomically viable means of introducing chirality is catalyst control. When it comes to catalyst controlled asymmetric induction, there can be three major pathways. One is metal catalysis, biocatalysis, and organocatalysis. Metal catalysis is something we can understand by the name itself. Metal catalyst or chiral metal catalyst introduce asymmetry into the molecule. Biocatalysis is something that is facilitated by biomolecules such as enzymes or peptides, for example. Organocatalysis is something that a third pillar which came into existence recently. The former two processes are existent even before the organic catalysis came into picture. The real organocatalysis came into picture, but organocatalysis is something we are going to talk about a little more in detail. But this has significant advantages for the former processes in the sense that the organocatalytic means are more inexpensive compared to the other two, and also non-toxic. That's most important aspect that is associated, and indeed that made organocatalysis more popular than the other two. So once we talk of organocatalysis, we should know what is this organocatalysis or organocatalysis as a process. Organocatalysts are those which are typically composed of elements such as carbon, hydrogen, nitrogen, sulfur, and phosphorus. Okay, these molecules usually we know by the definition of organic chemistry itself. These are called organic molecules, which are composed of these elements, right? So that also tells us the molecules which are composed of these elements, and those processes catalyzed by these molecules is what is organocatalysis. Okay, why it is popular? I already told you a little while ago. These are robust, inexpensive, readily available, and non-toxic. Okay, these are the advantages of organocatalysis or organocatalysis. Okay, so one more distinct feature of organocatalysis is that these processes, involving organocatalysts don't require demanding conditions such as what typically are employed during metal catalyzed reactions. What are demanding conditions? I mean to say, you don't need inert atmosphere, something like nitrogen, oxygen, nitrogen or organ atmosphere. You don't need low temperatures. Usually, of course, low temperatures are employed in organocatalysis, but that is for the sake of enhancer selectivity. Okay, but usually it is not required. Okay, absolute solvents. I mean, absolute solvents. I mean, so dry grade solvents or anhydrous solvents. We mean to say these are not usually required. Okay, another important feature in the context of non-toxicity that I mentioned already twice in this talk is this is more relevant in pharmaceuticals. Pharmaceuticals means the drugs or medication or the related compounds that are of direct implication to humankind. This obviously are something that don't tolerate metal contamination. So organocatalysis thus offers an efficient means of preparing pharmaceuticals free of metal contamination. So this is very briefly about organocatalysis and advantages. Okay, these are some of the organic molecules, okay, that are typically employed in synthesis. Okay, so don't think that these are the only things, okay, only molecules that are employed. Okay, these are only representative. Among them, these two molecules that I highlighted on this slide are the ones that actually gave Nobel Prize for example, the top molecule, proline, that gave Nobel Prize to Professor Benjamin List, and oxazolidinone is responsible for the Nobel Prize to Professor MacMillan. Okay, the other molecules, as you see, some of them are modified or non-natural ones. Some of them are natural, or otherwise I use the word from now on, if at all I use, that is chiral pool material. Chiral pool material means what nature produces the molecules in chiral. So for example, you see the first two, proline, quinine, these two are chiral pool materials. Nature produces them in the same native form. The others are modified versions of natural products. Okay, or prepared or artificially prepared compounds or catalysts. Okay, so in this context of the particular talk, this is what is most important transformation, which was reported in 1971. This reaction is named after the two groups of scientists interestingly, both are from industry. One set of people, Hajos and Parish, and the other group of chemists are from another industry, Eder, Saur, and Nishat. Okay, what they've done, you see the particular transformation here. They took this triketone. Okay, this is a racemic triketone, and performed intramolecular aldol condensation or aldol reaction. This is a condensation product. This is aldol reaction product. What is most impressive about this particular transformation? Of course, if you want to convert 1 to 2 or 3, you don't need necessarily proline. Okay, you can use any other typically readily available base. But what is impressive about this particular transformation is, in addition to the yield, the enantiomeric excess that was obtained in this molecule. The racemic compound was transformed to chiral material in excellent enantiomeric excess. That is an impressive feature. This was reported in 1971. They proposed the transition state as it is shown here. Okay, you can see what was proposed. This hemiaminal, you see where this proline is here. Okay, proline was understood to be generating this hemiaminal, and the enolate that is originating out of this ketone, that the terminal ketone, reacting onto this hemiaminal site and thereby leading to the cyclization. That was the proposal. Although it was possibly the hypothesis of these particular authors, it didn't go well with the community, with the scientific community. Okay, for whatever reason, subsequently this transformation didn't receive much attention for unknown reasons, or known reasons, or unknown reasons. So, but otherwise, if you see this particular compound too, this is what is called Wieland-Mischer ketone, has excellent applications in steroidal synthesis. You see these two cores, are two rings. These two represent the AB rings of, for example, if you know or if you remember the cholesterol or sterols as such, the AB rings that this represents. Okay, after this 1971 discovery, there are very few reports subsequently that involved proline as catalyst and utilized for enhancer selective transformations. You see one that was reported in 1976 by Danishevsky, where this triketone was subjected to intramolecular aldol condensation using proline, obtained 26% enantiomeric access. Of course, later, after some efforts, this enantiomer selectivity was increased to 86% by the utilization of this phenylalanine, which subsequently elaborated to estrone. Later, by Woodward in 1981, utilized this reaction, that is intramolecular aldol reaction, catalyzed by proline, in producing these two diastereomers, compounds 2 and 3, in moderate enantiomeric excess. That was with L-proline. Interestingly, what they found was with D-proline, the enantiomer selectivity significantly improved. Okay, this is a case of match and mismatch. Okay, although the authors at this point didn't claim, but this is a typical case of match mismatch of catalyst versus the substrate, because the substrate already was a chiral material. The match mismatch between the particular form of the catalyst made the difference here. Nevertheless, when they took the racemic one and treated with the chiral proline, they got 36%. This was the maximum E that they reported, which was eventually extended to the synthesis of erythromycin. A respected scientist from Indian community also contributed to this chemistry from University of Madras. This particular triketone, this is a representative of Professor Swaminathan's contribution. This is one, because of paucity of time, I took only one paper, but otherwise he had contributed to the other studies involving proline catalyzed chiral transformations. In this particular instance, you see that Professor Swaminathan also did the aldol condensation reaction, analogous to Hajo's-Parrish reaction. But what is interesting in this particular transformation is use neat reaction. There are no solvent associated with this particular transformation. You see that this is effectively a solid phase kind of reaction. Although if you read the paper, you will understand that depending on the kind of substrate that he employed, depending on this N, I mean to say, it was homogeneous or not homogeneous. But eventually he obtained this product. What he proposes the transition state to be a synchronous activation or involvement of the acid and amine functionality leading to the intramolecular aldol reaction. Okay, so but somehow this model also was not very well accepted by the synthetic community at that point of time. So now we're actually moving to the topic. The story behind the current development by List and co-workers is this particular aldolase chemistry. So you can see the paper that I cited at the bottom, Barbas and co-workers. You see the title, especially I pasted for your sake, efficient aldolase catalytic antibodies that use the enamine mechanism of natural enzymes. So nature employs aldolases for the construction of carbon-carbon bonds. This is the primary enzyme that nature uses. And carbon-carbon is fundamental in the formation of molecules such as whether it is amino acids or carbohydrates, especially carbohydrates and related molecules. So if you see what Barber's group, you see the science paper in 1995, you see the timeline. They have expertise in developing or modifying aldolases and employing them in catalytic manner to bring out various organic transformations. And they proved through several studies that this reaction involves enamine mechanism. What is that enamine mechanism? They showed that the enzyme having a lysine residue, having the terminal amine group, was responsible for the formation of iminium ion with the reactant, and subsequently that undergoes tautomerization to this enamine, which eventually undergoes aldol reaction with another aldol acceptor, okay, and thus releases the product. This is how the catalytic transformation was reported. This was way back in 95. Okay, but this particular hypothesis was the basis for what we are today learning about, the so-called modern organocatalysis, which was introduced by List, Lerner, and Barbers in 2000. Okay, so what on the basis of the aldolase chemistry, what I just mentioned, that they realized that amino acid residues are responsible for the formation of imines and enamines, which eventually made the basis for the consideration of the fact that the amino acids in chemical environment also, that was in enzymatic environment, in chemical environment also possibly can do this kind of transformation. Indeed, that is the basis. And List was the postdoc with initially with Barbas. Fortunately, I was also associated with Professor Barbas during my postdoctoral tenure during 2005 to 8. So List initially joined as postdoc. Then he was offered assistant professor position at Scripps Research Institute. This was his first work in collaboration with Professor Barbas. And you can see a representative reaction I showed. Proline catalyzed successfully the intermolecular aldol reaction, leading to healthy yields and very good enantiomer selectivities. It is only representative, that is 76% enantiomeric excess. So what is important here is this particular sentence mentioned by List in that particular JAX paper. What is that? I'm reading it for you. The development of aldolase antibodies that use enamine mechanism and accept hydrophobic organic substrate has demonstrated the potential inherent in amine catalyzed asymmetric aldol reactions. And he cited reference 4. You can see reference 4 is completely of Barber's papers. So that tells you that Barbers established this antibody chemistry, enamine mechanism, and also the reactions, relevant reactions on organic substrates, which is what I sometime back mentioned. Okay, you also note the time of submission. Purposefully I mentioned, I'll talk to you why I mentioned this. This was accepted and published online on 26 February 2000. This is a mechanism which goes in line with the antibody catalyzed reaction that I talked to you a little while ago. Proline forms imine or enamine, as you see here, which subsequently undergoes aldol reaction via this transition state, giving the carbon-carbon bonded aldol. Eventual hydrolysis releases the product and regenerates the catalyst. Okay, so this particular transition state is actually important and widely accepted. Eventually was validated by Hawke and co-workers. Hawke is a famous computational chemist who validates the organic transformations computationally or theoretically. So this is, you can see that this reminds us of a Zimmermann-Traxler model that we usually learn to explain metal catalyzed transformations, but this is a metal-free version of the Zimmermann transition state, and this was responsible for the enantiomer induction. You can see that one anisotropic phase is covered, covered in the sense covered by the nucleophile that eventually attach the electrophilic site from the re phase. That is, re phase is effectively the phase that is behind us. What we are seeing, the RCHO, is the C phase. Okay, so re phase is behind our view of this molecule. Okay, so this was I'm just showing you one application of this particular technology, that is intramolecular aldol reaction, which was used for transannular aldolization. This was the transition state proposed, and you can see this was employed for the asymmetric desymmetrization reaction. You can see that List utilized the fluorinated proline to obtain this product. The triquinane eventually was elaborated to the synthesis of the natural product quercetin. Okay, then comes the great chemist MacMillan into picture, and the purposeful reason I mentioned, as I said sometime back, why I mentioned the year of date of publication. Okay, you can see here that this was published in on 15th April 2000. So if you remember the earlier work, that List work was published in February, and the same year, April, MacMillan published this chiral imidazolidone catalyzed Diels-Alder reaction, where he obtained excellent enantiomer selectivity and a very healthy endo-exo selectivity. This is only a representative example. There are several other substrates that he dealt with. This catalytic system primarily goes through iminium mechanism, And through Iminian mechanism, one can accomplish not only the Deal server chemistry, several other types of cycloadation chemistries, and also Michael type reactions, which I'm avoiding for the sake of time to explain. But what MacMillan proposes is that MacMillan thinks that, or MacMillan at that time thought that this is analogous to Lewis acid activation, where a Lewis acid typically activates the enol and subsequent Michaelidation or the insider chemistry. However, we accomplish analogous manner. This iminium ion also activates the substrate, and subsequent transformation can be accomplished. We'll see little while later the detail of this particular hypothesis. And this is actually the transition state model that explains the origin of stereoselectivity. This is real genius design, according to me. That is, this covers this particular group in this catalyst. What is most important is, of course, this catalyst is chiral. What is most important group in this catalyst is this benzyl group here. That group you can see here, CH2PH group, covers the one anisotropic phase of this iminium ion. It effectively stacks one anisotropic phase, thereby making the other anisotropic phase only available for the attack or approach of the nucleophile or the reactant. So in this case, you can see that the B phase is blocked by this benzyl group, while the C phase is open. That is the responsible for the origin of the stereoselectivity. Here also, I'm only explaining very briefly the application of this hypothesis in the synthesis of complex natural products such as solenopyranone D, which was reported in 2005 by MacMillan group. You can see that
In simple languages,
was
they
accomplished via the intramolecular Diels-Alder reaction using this imidazolidone catalyst. And here it is an intermolecular Diels-Alder reaction between the colored portions. You can see the diene and dienophile, giving this tricyclic structure eventually was extended to the vincorin, a natural product. Sorry. Okay. This was in 2013. Okay. Now coming back to this. Okay. I have only 2 more slides. Please don't worry if at all I don't see the time here. But otherwise, this iminium catalysis, as you see, reaction of the carbonyl with proline kind of secondary amines forms enamine. Of course, imine followed by enamine. Iminium ion formation or enaminium chemistry involves primarily homorizing activity. Okay, we know whenever reaction occurs, we learn of these homo-lumo interactions, right? So obviously that the gap, the homo-lumo gap, is tuned by this catalysis and the homorizing. Okay, there are 2 ways of accomplishing it. Either one can decrease the lumo or one can increase the homo. So here homorizing activity occurs by the formation of enamines. That leads to the high reactivity of electrophiles. You can see that once this homo is raised, the distance between the homo-lumo coming down. Similarly, on the other hand, the iminium chemistry, that this is the top one is list chemistry. Okay, the bottom one is iminium chemistry, that is by MacMillan. Okay, which we just saw briefly. Okay, what this involves? This involves LOMO lowering activity. What is the LOMO lowering? You see the difference. The HOMO is raised here, but here HOMO remained the same level. But it is assumed that the LUMO is something that is lowered in this case. That leaves high reactivity towards nucleophiles. Okay, whether we are doing this activity or HOMO rising or LUMO lowering, what is essential for us is a facile chemical transformation. That is what is achieved through these 2 means. And for this technology and for this contribution, List and MacMillan were awarded the Nobel Prize. And for your information, although I mentioned the contribution of Barbas unfortunately passed away in 2014. So if he would have been alive, he would have been possibly a 3rd Nobel recipient, according to my understanding. So the impact you can see of these discoveries in 2000, there was 1 or 2 reports which I described. You can see how exponentially the growth in this field has grown. Okay, so you can see that eventually now where we are in 2020, you can see how many contributions on this particular organocatalysis. This was arrived at from the source I finder by giving organocatalysis as the term. Okay, and this not just about number of publications. Don't think that Nobel Prize will be awarded just based on number of publications. This is based on the impact, as the title of this particular slide says, impact that it created. This left significant impact on the science as such, in terms of pharmaceuticals, in terms of natural products, in terms of achieving drug candidates. Okay, so with this I'll conclude. So what I try to explain to you is that a third parallel was established. What is the third parallel? The first two being the metal catalysis and biocatalysis. Third parallel in the form of this organocatalysis was established, and the advantages of this process being primarily this is metal-free scenario, and also many of these organocatalysts can be easily derived from chiral pool materials. Okay, this technology was widely applied in new method development in organic synthesis, natural product synthesis, and also synthesis of pharmaceuticals. Okay, and don't think that because Nobel Prize awarded and it is done. No, this field is still thriving. Several chemists abroad and Indians also pursuing this chemistry. Okay, one prominent chemist that actually initiated the imine chemistry in India is Professor Vinod Singh from IIT Kanpur. He made significant contribution. Indeed, there is a catalyst on his name called Singh's catalyst. Of course, I don't mean to say that others are not, but there are several other prominent chemists. Obviously, I can't get into the names of individuals due to the paucity of time. But the reason I mentioned or I cited this particular paper, which was compiled by Professor Ramachari and Dr. Silvi from University of Hyderabad. You can go through this PINSA paper, Proceedings of Indian National Science Academy paper, published in 2020, compiling the contributions of several Indian authors in organocatalysis, especially. Okay, we also pursue to a certain extent organocatalysis, but our catalysis is not based on imine chemistry. We work on organophosphine chemistry. For details, one can go through our webpage. So I had the great opportunity to meet Professor List a couple of occasions during conferences. This photo was especially taken during a conference in 2015 in Hyderabad. That was me, believe me, that was me. And I had more hair and possibly more black hair. Okay. With this, let me thank sincerely the Cogito. Okay, I think, is it something wrong? Cogito. Okay. Sorry. I think that was what was mentioned in the email I copied. I think there's probably a word missing. But anyway, nevertheless, let me thank the Cogito team for inviting me and giving me this time. Thank you very much.
Thank you, sir. This was a really interesting talk, and it was really fascinating to see how this discovery has impacted how we understand the
Yeah.
known
By the way,
world.
I didn't follow the time. I hope I was on time. Did
Uh,
I?
no, it was on time. Yes, sir.
Okay. Okay. Thank you. Because I couldn't see anything. The screen was full of my slides, so I couldn't follow the time.
Yes, you can stop presenting your screen now.
Oh, okay. Fine. Is it fine?
Yes, sir, it's fine.
Okay.
Aditya, do
Okay.
we
Yeah.
have any questions?
Yeah, so there was a question. I'll just say you mentioned in your slide that organocatalysis is a slow or sluggish process. Is it possible to speed it up in any way?
Right, right. See, slower sluggish means it's not all processes. Okay, one of the drawbacks. Okay, so obviously, every one of us understand that no chemical reaction, no chemical process to that extent is ideal. Okay, except what is done by the nature. Okay, so no chemist so far could approach anything closer to nature. I mean, you may criticize me, but I'm true. Okay, so what I'm trying to say is every process, although organocatalysis provides an excellent means of achieving some of the challenges not met by metal catalysis or biocatalysis, but otherwise this was one of the drawbacks. But when I said sluggish or slow, not applicable to all reactions. And whenever one wants to speed up the reactions, there are means of doing it. That is solvent is something that plays a role. Temperature plays a role. Okay, and indeed, of course, sterics electronics are something that one can play with to deal with this particular issue.
Okay. Are there any more questions?
No, there are no more questions.
Okay, so with that, we will conclude this talk. Thank you, doctor, for joining us today, and
Yeah,
thank you for your
yeah.
amazing talk. And
Thank you.
we'll see you guys in the next episode of Nobel in Focus. Thank you, everyone, for attending. Goodbye.
Thank you very much. Thanks, Isha. Bye
Yes.
bye.